Okay, hello, good morning, good afternoon for Italian people, good afternoon, and welcome to ARP. Um, Good, we have a lot of topics to discuss, several topics. Let me start with, good news and bad news. I don't know which you prefer first. Um, well, good news. Good news first. Good news is that the theoretical, not all completely theoretical. In any case, the course arguments are over. So you have near the end of what you are asked to learn. In particular, here it's the old subjects that produce coding from you are over. So everything is finished. We have just an additional topic. We will start today if we have time. Otherwise, we will start tomorrow. But the last pack of slides regarding POSIX, the last POSIX subject, that is the shared memory model. I will explain, and you are asked to learn how it works, not to write programs regarding it. There's nothing new in particular with respect to what you have already done, and is very similar to the contents of the thread programming model that probably you're doing in the real-time course if you attend this course. So it's the process version of the thread model, so with the shared memory. I just want to show you, and I want you to learn which are the specific differences, which are the similarities with all the IPC models of communication that you have used. So no coding regarding that, but I'm asking you to learn, in any case, the model. So also to answer questions at the exam or everywhere. So this was the good news. Good news, since nothing new you will have to learn and to practice. The bad news, well, it's not a bad news. It's you already knew that you have to do a second assignment, and you have to conclude very soon. The second assignment is simpler than the first one, not only because it's the second one, but also because you have already discussed it in class some parts of the solution. Not exactly the same for this model, but the components are very similar. So and one of you, the well-known Marco Fedozzi, has uploaded, not scared, is not timid, but I'm just asking all of you to do the same thing, or to answer, to pose questions, anything. But I think it's a very good support for everybody. I just gave a quick look, and I think that the material is good. So I'm not signing it as it is. I will watch with more attention, and if there's something that is needed, that I want to notice you, I will do in any case. But as a matter of fact, as a starting point, it is very useful material. So bad news simply that you already know what is the second assignment. I will comment it now, starting as a new topic. But if you have watched the video clip, you have a description of the problem. And I think that 2 weeks are absolutely sufficient for terminating and uploading. So I will put it with the same system of the first assignment, a soft deadline with the same rules. So in any case, if you are late, you will have small penalty. In particular, I know that some of you are still struggling with the first assignment. I appreciate that, and I'm trying to support you, those of you who are still working on that, as much as possible. Keep on doing that. Doesn't matter if you deliver and you're late, but do it. It's really important. I've seen that some of you did upload in a draft version. I suppose that they will conclude and will transform the draft version on the website, on the repository, in a final version. So please do that, even if you are late. Don't be scared of that. Okay, so good news and bad news are over, but I think that the bad news are not too bad. The problem, just probably you have watched the clip. I shared the screen with the desktop. I will open the file. Okay. So this is the problem. It's a problem that inspired to a thesis, good thesis in Japan that we assigned some years ago to the double title students. Consider that this doesn't seem a robot, but it is a robot. Yes, it is, because it is a robot, a Cartesian robot with 3 degrees of freedom, because it moves in this way. This rail moves along this direction, and of course there is the z-axis. The only axis you have to take into account. So you have just to develop 1/3 of the system, the system that is completely remotely controlled. So it's has no intelligence except for the fact that it takes into account, probably it has intelligence in the control of the motor and the position and so on. And so you have to design this architecture with an mandatory, compulsory. It's compulsory to have 2 different computers. How can you have 2 different computers? Well, I've asked before the lesson started officially if some one of you has already activated the on-cloud virtual machine. It's important. This is one way of doing that, but not the only way. After I will explain. If you want to, so it's not necessary to develop this software and test and make it run on the virtual machine. But I suggest you to do that, because so you will become confident and learn exactly how to use the virtual machine, since the 3rd and last assignment will be necessarily on the virtual machine, because you have to connect your virtual machines, the individual virtual machines, with other students' virtual machines. So I suggest you to start exercising your ability of working on the virtual machine. If you are, in any case, even if you use the virtual machine, most part of the software, or 99% of the software, should be written and tested on your computer. And once you know that it runs properly, you upload on the virtual machine. You might also run directly on the virtual machine by editing the only difference is that you don't have a graphic interface. You must use the shell, and all the shell instruments, like an editor, local editor. So you may also work developing all the software in virtual machine, but I suggest not to do that, to spare time, since you have a lot of time for the virtual machine, but you will use in the next semester and in the next year. So spare your time. So it's better to upload an already running software, but you have to debug, to develop, test, debug completely on the computer. When you are on the computer, you simply have to run two sets of processes separately using two separate shells. One is the what I've called computer one, and the second is another shell that runs those two processes that probably, but it's up to you, are just in origin one process that starting as forked and executed two separate processes, or three if you want to follow the model of having a master and two to sub-process. For example, here a master process with one that forks twice, one for generating the scheduler and socket server, and the other one for generating this. But it's not necessary. You may simply run one process that, for example, the socket server that forks H, or H who forks S. But that's the model, on simulating the fact that you're on a separate machine. And this is another process. One question, maybe a frequently asked question, is typically, is it possible to connect through a socket two processes on the same machine? Of course, yes. The answer is yes. And the exercise, the code that you have in the tutorial on sockets on our web, that you can copy, paste, compile, and execute directly, is exactly of this kind. Two processes, one client and one server, running on the same machine, connected through a socket. Socket can connect processes on the same machine and different machines. You know that this is an important question that has a trivial answer, but probably it's better to remind you which is the solution, which is, the question is, which is the address of this machine since to connect client and server, you need to connect through the IP address and port number. I assume that you remember this. Which is the address of this machine? You have two possibilities. One is to use the IP address of the machine. If the machine is connected to internet through a provider, has a local address, and it's simple to discover which is the one. But the correct way of doing that, the proper way, the simplest way, is to use a conventional address, that is a reserved IP address, which is not available on internet, is 127.0.0.1. If I remember correctly. Well, sometimes I forget the number. In any case, there is a conventional number. I will, during the polls, I will check if it is. So this number, if correct, it's conventionally an alias for the IP address of the same machine in which you are running all processes, okay? So for implementing this, you'd better use this address if the processes are on the same machine. If you are on different machines, well, let me, later on I will, well, I will, not exactly, I will show, I will, yeah, okay, I can also show an example of this. I will show you how to run the virtual machine as soon as you have configured it. But in any case, you know, just to conclude the presentation that is on the video clip, so go back in the video clip and see that the man here, the operator, man or woman, maybe a woman operator, has 3 control actions. Start the motor upwards, increasing Z. Start the motor, decreasing Z, or stop any moment. So it's supposed that the operator is supposed to see what is happening on that hoist, on the crane. So it says, just like having the teach pendant has a button to stop. But on the screen, you must have feedback values. That is just, if you don't watch the hoist and don't see what's happening, you continuously have the value of the Z axis. 1 value every second during motion. So, of course, the value must be sent by S, and S in its turn must know the value by H. H is the process that runs the motor. And if, just in case you don't stop before you get on the end run, the motor will stop and says, oh, end run. Okay, so 3 feedbacks. Z axis, 1 per second, and asynchronously end run if the end run is reached. So H has to simulate the behavior of the motor of the Z axis. How to simulate? You must simulate using a loop, which is able in real time, 1 per second, to send the coordinate, to send back the coordinate, and increasing or decreasing the coordinate, and to detect the end run, and this, in this case, to give back the end run. So that's all. These are some figures just for the simulation, but absolutely non-strict. They're realistic figures of a small hoist in a workshop, 2 meters height, and the speed, vertical speed, both in upward and downwards. Usually there is a screw gear, so the speed is constant in both directions. As, for example, 5 centimeters per second. So you assume that every second you will see the coordinate increase or decreasing a value of 5. That's all. Is it clear to everybody? Questions? No questions. So I think that you know.
One question.
Yeah?
Maybe because I didn't hear it properly. It sends the coordinates back to computer 1?
Yeah.
Okay.
Let me. It was this one. So H manages the coordinate. because it's simulating the motor in the simplest possible way, and as the task of sending back to S the coordinate or the end run reached. So in case it stopped because it was outside the 200 meters of the work operation, sends, okay, I'm stopped. And S communicates through socket this coordinate. Okay?
Okay, thank you.
Excuse me, Professor, I have
Yeah?
a question. When we use the function socket, since we are testing on the same computer, on the same machine, can we also use for the domain AF Unix or AF?
No. You are in internet in any case.
Okay. So another question: when we in the structure of the server of the client address, the family field, we have to specify as AF inet, and for example, in the field S address, it is IN address any underscore any, right?
Yeah, I remember. Well, I think so. I don't remember by mind, but we can open the code that you can simply use directly. And so use just like you were in internet.
Okay.
Okay, no difference. Since if you want to, suppose that you have developed this system on your computer, you have two separate shells, two separate processes, they communicate through a socket. Then, for example, you upload on the virtual machine the computer 2, and they communicate through internet.
Okay. And
if possible, and I will, with some disclaimer, I will tell you after. Okay.
Okay, thank you. And the last question, if I may, you specified the 127.0.0.1 address, but in the code we used the function, if I don't remember, sorry, get host by name. If I don't remember, we use a function.
Let me check. I will share the screen. Desktop. Okay, not this one. For example, here.
I think it was in the client, if I don't remember. Okay. Yeah, it is server equal get host.
So IFNet?
No, it's
sock address server. No.
Server get host by name, right?
Okay. No, it's well, but it's argv1, so it's you must pass. It's one of the argument of the process once you run it.
Yeah, and I was wondering what would be the argument, because
the number.
I found that. Sorry.
Just the IP address.
Oh, okay. So the IP address you specified before.
Well, servers, you get us by name. Yes, argv 00 port and number. Yes, okay. So you run with the first argument is port number that you may decide. You know that you decide, you can choose the port number by yourself. a high port number, for example, 5,000. Sometimes I use 41,000.
I use 50,000.
Okay, you use
50,000.
50,000. Okay, it's okay. It's okay. Use on the server. So to connect to the server, you must specify as a first argument argv0 the port number,
Okay.
and then the IP number.
Okay.
Directly the IP number. In that
Yeah.
case, 127 and so on works.
Yeah, it's the local host basically.
Yes, the local host. What is called local host.
Okay. Thank you.
So, any other questions?
Yes, Professor. I would like to ask, when is the deadline for this assignment? Because I haven't found information.
Well, the deadline will be not the end of this week, but the end of next week.
Thank you.
I will write it, or just to announce it, asking you if there are problems. I think that 2 weeks are absolutely sufficient, since the most part of the work should already have been done, in a sense that you have clarified which is the problem. Last week, we have pieces of code just to copy and paste and so on. So it's not a complex task. I think it's appropriate. So we will have time in the last weeks of the course to talk about the third assignment in general, and to discuss all the topics of the course, just to have a sort of discussion and question and answers and so on. So not the end of this week, the end of next week, the soft deadline, just like the first one. Okay.
Thank you. Yes.
I've asked, I ask again, because I asked it before starting regularly the class. I ask again, did some of you already experimented the virtual machine on cloud or not?
I've just configured it, but not try to connect.
Not try to. You have to. Who are you? Matteo Azzini, correct?
Yeah.
Okay. You have to.
I'm waiting. I was waiting for assignment then.
Yeah. Well, so I think it's a good idea just to have a look at what is the splash screen of the virtual machine, just to have an idea. How can I do it? Okay. Oh, just before the class, I've jumped in this is the main page. Once you have configured the machine, for configuring your machine, configuring the machine is very simple, because you follow step by step what Professor Recchiuto has said in the tutorial. The only thing is not clear, because you have to pay much attention, is how to go into the Azure page. Since Professor Recchiuto tells the name of the page, and you can see the address of the page in the screen, but the screen is small, low definition and so on. But if you stop YouTube, and you can watch and see exactly which, and listening to what Professor Recchiuto says, you can understand exactly which is the web address of the page. If you don't catch it, ask me and I will explain. Just after having registered yourself and on the UNIGE webpage. Once you have configured step by step, with there's very few information to write. This is the main page in which you have a machine. You see that is a Linux. All the information, or well, let me display this. The virtual machine is here. The name of my virtual machine is ARP teacher, Linux, Ubuntu server, version, and so on. There is a local address on the local network, but which is really important, and you must use this for the third assignment, and also if you want for this assignment, is the public IP. So with this IP address, you can connect to the virtual machine, and you can implement the socket server.
I'm not sure you're seeing what you're seeing.
You don't see?
We just see the desktop with some icons.
Oh, I'm sorry. I'm sorry.
I thought it was it, but I'm not sure.
Sorry. Sometimes I do this. I'm sorry. Well, okay. This is the main page of the Azure. This is the definition of the machine. It's absolutely standard, nothing. The only, and you see here a public IP address. This public IP address is public in internet, so you can reach the machine in this way. And when you shut down the machine, you must do that. You see here, avvia, start, and arresta, stop. You always have to stop the machine after you have used it. Otherwise, you consume your money. And it will ask you if you want to keep fixed this address or not. I suggest to keep fixed, so will be always the same. Any time you start the machine, you will always find this. So if you have written a software which connects to this IP, it will keep on working, because you don't have to specify any time a different IP address. If you don't fix the address, anytime you start the machine, you will find a new public IP address. So no logical difference between, but it's easier if you keep always the same. And that's all. If you want to, how to connect to this machine, there are several ways. The Professor Chiuto, well, copiato. It shows you. Now I think that I can, scrivania. Okay, can you see the shell window?
No, we can.
No, you can't. So I have
only
to.
the desktop.
Only the desktop. Stop share and. Okay, the shell. Okay.
Yes.
Yes.
Usually I connect using the SSH. this address, and okay, it doesn't connect because I didn't start the machine, of course. I'm starting the machine. You don't see it, but I have to wait. Okay, I've seen on the other screen that the machine is working. So I can connection refused. Wow, fantastic. Oh, yes. Okay. So this is a, oh, the password, sorry. Good. You still see my shells window?
Yes.
Okay, so you see, now I'm connected using the SSH protocol. The SSH protocol is a remote shell. It's called with the SS because it's a secure shell. So the connection is secure, is encrypted, so nobody can break the connection on or spy what you are doing. The secure shell is on port or protocol number 22, and I've specified in the command the port 22 because by default my secure shell in my computer has a different port, but it's my usually you don't have to do that normally. By default, if you write SSH your name at the address like I did, it's all. You have to run, of course, the machine. So now I'm working on the machine. You see that I have a server. The server is the one I have implemented. I have compiled on the machine and run, so I can make in connection the client in well, I can do if you want, if you like, I can. Would you like I run the client socket client on my PC connecting to the socket server on the virtual machine? You want to see that, or you think it's in?
Yeah, why not?
Yes, please.
Well, I hope it works, but in any case, no, normally it works. A new shell. So I'm here. I have to go on the directory where, no. Okay. I'm looking for the executable. Don't remember where it is. Client. Okay, the client is here. So if I have two shells. I have just opened two tabs here, but if, as a matter of fact, there are two shells. This is the shell on the virtual machine. And the okay, slash server 2, okay, port, okay. Server 2, well, this is the server, enhanced server that forked, but it works in the same way. The port, okay. So the server is running, I don't know where, in the cloud. Here I can run the client port 41,000, and the address, I think I still have the, okay. Invite argument.
I think maybe address and port should be swapped, because I think for the code the port is the ARC's.
Maybe I don't remember. Okay, yes. So enter message, hello. The answer, okay, you see here that the server has received hello, okay? And the client died. So the demonstration is finished. Okay. Did you see the how it works? How did I do the thing? There are two ways. One is simply to transfer the executable. The executable is can run exactly on the other machine because there is the same operating system, or I just decide to compile and run on the virtual machine just to check if the compiler is the same. I found that there was no GCC compiler, so I've installed GCC compiler on the virtual machine, but okay, you can also install everything except for graphic interfaces, because there no graphic interface with the virtual machine. So this is the way it does. I exit from the virtual machine, exit. So connection to this machine is closed, and I can, well, let me share the virtual machine. So you see, now you see the page of the Azure page. Do you see it?
Yes, Professor.
Okay.
Yes, we can see the web page.
You see that is running. Arresta. Probably you have the page in Italian in any case, and Arresta is the important. Arresta questa macchina virtuale. Yes. In a few seconds. It's not already. Okay. In any case, is over, and you see that the address did not change. The first time it asked me to keep the address fixed. I said, okay. It's what is it? Was it this? Macchina virtuale? All right. Well, it's still stopping the machine. So you think that stopping the machine is not immediate, but you will have feedback and everything here. Okay. Now it has been stopped. You see here that Avia start can be selected. That's all. That's all false. Well, I think it's a powerful way of working, and I think it's a professional skill that is important to achieve. So please do it as soon as you can. You have a lot of computing time, so if you don't waste it, you can use the machine with many experiments in this course and in other courses. Do this, and I suggest you, even if it's not necessary for the evaluation of the second assignment, I strongly suggest you to do the exercise to develop and to test, to run in your personal computer, and then to upload the server so that the hoist is in the cloud. So the slogan is put your hoist in the cloud, okay? Not necessary for the evaluation, but do it. So after you have succeeded in doing it, you will be able to solve the final huge assignment. Okay. That's all. Hope. Questions about the virtual machine?
Well, we use the virtual machine as the computer with the hoist, with the processes.
Hoist on the virtual machine.
And our computer is like the remote control of the operator.
Exactly. So it's in a sense, is a more close to reality, to some real applications in that case. Okay.
Yes, thank you.
Your hoist may be a hoist on a Mars station with the rover, so you're distant. You remotely operate that. The principle is similar. Consider that this system is used to control satellites and other flying objects in general. Not exactly with the IP address, but the idea of socketing is exactly the same. So the skill you're learning can be employed in a large variety of situations, including automotive field. Well, a couple of minutes of pause, if you may ask you. I will go on with the next topic. Okay, just a couple of minutes. Okay. Shall we start again? Thank you for the break, little break. Well, as I told you, we don't have many new arguments for the course. We have to discuss what we already know, and I wanted just to share what I've learned by interaction with you, discussing the first assignment with the questions that emerged in discussing with several students and so on. Okay. Can you hear me now?
Yes, Professor.
Okay. Thank you. Just to be sure that I'm not talking to nobody. I've written here is this file shared with the frequently asked questions assignment 1?
We see the folder, I think.
You see the folder in any case. So I didn't learn exactly how to use the sharing. I'm sorry. It's too complex for me. Share the screen. No, now first I have to open. Okay. Then I have to share but I don't have, the problem is that I don't have, okay, it's not necessary to share anything. I will read and comment and give you some comments. One, the first problem that some of you found was the how big can an array be declared in C language. Well, it's a general and abstract question. Is not related just to this assignment. The problem arose because some of you decided on the process R to receive all messages, to put on a large array, and at the end of the reception, transfer the whole array to M. In this case, if you put in one array all received messages, you will have a big array, because if you receive at least 1 million messages and 1 million, and every message is several numbers, you will have an array of several megabytes. And some of you found that was not able to reserve an array of such dimensions. This is a general problem, so it's a good idea to discuss briefly. Well, recalling, this is a general problem in the C language, in C++ language, C and C++, and in all declarative languages, all procedural languages in which you can reserve memory in a static way. I remember these concepts. C language has three kinds of memory: static memory, dynamic or so-called automatic memory, and really or dynamic memory. The third one, which is usually called by default dynamic, is the memory that you get in C language using the alloc or malloc system function, and in C++ with the new construct. This is a true dynamic in the sense that you allocate this memory, and once you have finished using the memory, you deallocate using the dispose or the similar function. You have to do that because otherwise you keep occupied memory without using it. This kind of memory that we don't use in our course. Remember that in low-level programming, in embedded systems, in programming the hardware, programming the electronics, or writing pieces of the operating system, or real-time parts, in general, real-time programs, you don't use dynamic memory. Why don't you use dynamic memory? Because dynamic memory is allocated on an area that is called the heap. The heap is big, but is managed completely by the operating system, by the kernel itself. So every time you dispose, so you give back the memory you have allocated, the operating system marks the area, maybe a big area, megabytes, or simply small areas like kilobytes, as disposable, but the operating system has to find all unused pieces of memory, put all together, and keep them already available to new allocation. This process is called garbage collection, is a part of the kernel, how to manage garbage, because if you have disposed, you have given back dynamic memory, this is garbage from the point of view of the operating system, of the kernel. Garbage, since is a memory, has addresses, but is not directly used. So the kernel continuously carries out the process that is called garbage collection. The idea is to change to move all memories that are in use, so that the free spaces that are called garbages are big enough to be used again. It's a complex. It's similar to what happens in hard disks with the what is called the fragmentation of a hard disk, in which you have several blocks everywhere, free, but you cannot put all together to use for a whole file. So the defragmentation of the heap is called the garbage collection process, and is a heavy process with complex algorithms. And if you use dynamic memory, you force, but you do not see it, you force the kernel to do garbage collection. And garbage collection stops the scheduler, because it's a process that runs, it's a heavy process running as an administrator, or as a root, as the kernel itself. This is the reason why in real-time programming or embedded systems, embedded programming, so efficient programming that has to keep the to have deadlines, hard deadlines, or even soft deadlines, do not use garbage collection, so do not use dynamic memory, to avoid that the garbage collection process makes the system slow in non-foreseeable way. You cannot predict how slow, because you don't know when the system works. This is one of the reasons why Java is not used much in robotics and in real-time systems, because Java is completely dynamic. All variables are allocated in a dynamic memory. So Java has a strong garbage collector, and the speed of the kernel of Java cannot be hardly can be used when you have deadlines. So going back, in C language and C++, you have dynamic memory. We don't use them for this reason, not for simplicity, not for making you for giving you some easier task to develop, because this is the professional practice when programming at this level. Normal variables that you, in a function or in a main program, you declare a variable, int x, the simplest variable, int x. What does it mean? X is partially dynamic, so theoretically is dynamic in its turn, is not in the heap area, so it does not involve an unknown process, unpredictable process of garbage collection. Is dynamically allocated on the stack. The stack, you know, there is a part, going back and see the slides with the Linux architecture. The stack is a part of the process. The process has a stack, and the stack is an area in which all variables, we don't put attention, we don't keep attention to that. But once you define a variable in the main, in a function, or in a block inside the main, this variable is allocated in the stack and deallocated as soon as you exit from the block. The block may be a block inside the text, maybe a function. When you have the final closed parenthesis, the block is over and the stack is deallocated. All the variables inside are deallocated. And when the main exits, all the stack, the main stack is deallocated. They're not static variables because they do not survive after a function returns, for example. Well, when the main returns, you don't need variables, so everything is deallocated in any case, but it has to do with the functions. When you have several functions, local variables and functions are on the stack, but you may declare variables that are really static, And this is the first mechanism, very rarely used in general, in which variables are declared outside the main. What is called in C language are called at file level. All variables defined on a file before you write the main are static variables, so that survive not only, well, after the main is terminated, also those variables are erased, but the static variables are permanently there, even if all functions return. Which is the difference? Usually we do not perceive that, but it's important to know, and in real-time programming is really important. And some of you has found this problem because they decided to, in the R process, to declare a big array for holding all messages. It was not a good idea. So many of you, and those of you who asked me what to do, I've answered, don't do that. There's no need. The R process, while it's receiving, can compute all the data that are necessary for the statistics. So at the end of the process of getting all data, R can transfer only the gross result of statistics to M. So not a large amount of data.
To be honest, the specification sounded like M was to compute
specification were not clear. It was written in this way just to see, well, there's no, it was not a mistake just to transfer all things to M, but you have to find out how to do that, because you cannot decide, you cannot define a very big array because the stack is limited. How is limited? That's the first question. Because usually it's similar to the problem of the dynamic variables. Since all variables declared on the stack can be deallocated, and this in any case makes this slower running of the process itself. If you have a large amount of variables, and it's better to keep really static, so they are allocated before the main starts, and of course de-erased after the main dies. So it's similar to the, not so dramatic like the real dynamic memory with malloc or with new, but in any case, this is a key point. So I wanted to do, if some of you discovered that this was a problem and how to cope with the problem. And the solution is asking the system, for example, now I have to share the screen. So the question is, how big is the stack? And can I change the stack dimensions? I assume that you see my shell.
Yes, we can see the shell.
Okay. There is a shell command that is ulimit with several switches, so several arguments, so you can ask the system how is the limits of the resources that you're using, and in some cases to change them. For example, you can see interesting information. Stack size, that is the fifth from the bottom. You see stack size is 8 megabytes. So the stack is not a huge stack. And so you can decide what to do. You can use, obviously you can, but no more than 8 megabytes, including all variables of the process and all the functions used by the process. You can increase, for example, in some cases. There are other information, so you can see, for example, that the data segment size. Data segment includes also static variables, really static variables, unlimited, perfect. Unlimited is fantastic. File size is unlimited. How many signals you can, let's see all the information. How many signals, pending signals. So if you send many signals to a process, but you do not execute them, do not react immediately, a lot of signals. You see how many. Max locked memory, max memory size, fantastic, unlimited. That's the principle of virtual machine. So you have access to the whole virtual address, 64 bits. It means I don't know how many gigabytes of memory. How many open files? Interesting. Open files, 1024 open files. And surprisingly, the pipe size is 8 blocks of 1/2 of a kilobyte. So the pipe size is small. It's small. So you cannot use the pipe for storing a long queue of messages. The pipe, very soon you will find the pipe full if you write without emptying the pipe, and so on. Okay, so there are many information on that. So the answer to that problem is either you increase the stack dimension, or you decide not to build a big array with all messages and to carry out some process inside R. That's a good idea, and to send reduced data to M. So this was the first and interesting question that several students posed. Another problem is the pipe dimension we have seen, and another problem was the select. What is the maximum number of file descriptors to check? You know, it is written on the tutorial. The first number that must be at least the pipes you want to check +1. You may simply write the maximum number of pipes of the system, that is 1024. If you foresee in advance that you will not, because there is the pipes, sorry, the file descriptors. This is the real number of file descriptors, not the number of file descriptors. I mean, if you have 2 file descriptors, one is the number 1 and the second is the number 1000, you must check, you must write here, right there as the first parameter, 1000 plus 1. So if you can foresee exactly which is the maximum number for a file descriptor, you may spare computing time of the kernel, because the kernel will take shorter time if you have shorter number of file descriptors to check, but it's absolutely not important. So this is the reason why it's common to write there just the maximum number of file descriptors, that is 1024. Another problem was in the select. Anytime you call the select starts from 0. So you have, in any case, to rebuild completely the set of file descriptors to check. So write the lines to 0, to put to 0 on the file descriptor, to set even if the set is the same, every time the select starts from 0. It is written on the tutorial, but it is important. who computes the statistics are, well, are M, if you want, if you are able to transfer all messages to M can compute the statistics, otherwise, and can R compute most part of the statistics while it receives data. How many data stop R? You may choose a number. I've told you at least 1 million. You can choose, it's not a strict specification. You can decide at least 1 million from at least one of the two generator, or 1 million in total. Or you may say, or may use a timeout system. That is a smart idea. If you don't receive any data after a certain amount of time that you decide, you stop, and so on. Or possible solutions are different. Another question arose with the, shall we use integer, float, double? Well, integer where it's needed to use integer, like in the time specification and so on. And in general, for all these problems, using double, well, float are old style programming. There's no reason to use float. You don't spare space nor time. It's not important. Sorry. Excuse me, there was an unusual telephone call. Double in general, or for any computation, use double. There's no need, just to avoid underflow, overflow, and so on. In general, in modern computers, also in small chipsets, double are at the same speed in computation than integer, than old integer. And the last question that I marked as the frequently asked question is debug messages. To debug a concurrent program like that, you need some messages saying what a process is carrying out. In a system like this, in which you have to measure time, you must not make the system run slowly. Otherwise, you lose what is happening. So it's not a good idea to frequently, for example, for G1 and G2, to send messages periodically or very frequently, because since they are asked to run at maximum speed, so to check which is the maximum speed, if you make them slow, you lose the possibility of measuring the bandwidth at the end. So don't put unnecessary messages just in critical point, and it's better to write messages on a file with respect to the shell screen, because writing on a file, as you have seen in the slides, uses a cache, so it's very fast. Not as fast as avoiding writing, but in any case, it makes slow, but not much slow. So put messages, diagnostic messages, in critical points in which the minimum critical point, to not to alter the structure of the program. Some of you used to write lot of messages and couldn't see the difference between the delay, some delay in the generators, because of course, because if you write frequently, the speed is that of writing, not of the delay you put on the generator. Well, okay, so I want to discuss also because some of you are still working on that. I think I want to make it easy as easy as possible, the work, even if you are late. So go on. Okay. Those of you who are working, please keep working. And now we can start describing the theoretical, the last theoretical aspect, the contents of POSIX. That is the shared model for communication, for IPC, inter-process communication. As I told you at the beginning of the class, I will not ask you to write code. You will find pieces of code that you can, if you want to copy and paste, compile and execute and so on. Maybe I will ask you some questions in the exam and about that, but no exercises. But you must learn these concepts. So open it is not loaded in Aula Web, but it will after this short presentation. You should see the okay. Can you see the shared memory slides?
Yes, Professor.
Yes.
Okay. Last way of making process to communicate. This is the idea. This is a process. You see the various parts of the process. A process has data. BSS and data are two definitions of, in any case, of static data. Static data, initialized and not initialized. The heap, the stack. And this is another process. The idea is that to understand this, you have to consider the process as an entity which is mapped into, is loaded into in the memory. These two processes, and suppose the two processes are simultaneously loaded in memory, in different parts of memory, of course. In theory, this happens, this also if the two processes are temporarily not in memory, resident in memory, because one of the two is swapped onto disk. But theoretically, it may happen, but logically, it is the same thing. So assume that they are permanently in memory, and probably you should know that they may not use successive addresses. So in memory, they usually are located in blocks, not side by side. So it is managed by the electronics of the system. So for me, owner of the process, my addresses, the addresses, memory addresses, start from 0 and end at the end of the memory I'm using. The electronics, so the memory manager, maps those addresses in different points of the memory, of the main memory, depending on which parts are free. Not continuously, they are usually allocated in blocks. So you can consider the memory as a sequence of blocks, not very big. Typical block is 4,000 kilobytes, for example, just like blocks on disk. So a file is logically sequential, even if its blocks, 4,000 bytes blocks, are scattered, are distributed everywhere on the disk. There is a central manager who decides that where are single blocks, and you perceive them as consequential. And the same happens in memory. We are interested in data memory. And so suppose you have a big array, an image, for example. This is typical of the communication between processes regarding images. When the memory area, which is the image that I'm watching on the screen in this moment, and you see as a shared screen, is an area shared by the process that is generating the image, the process that seeing the PDF file, and the process that is managing the screen, that manages the device driver of the screen. Because it would be very heavy to transfer an image that may be several megabytes anytime you change the image. The image is static now, except for the small frame in which I see me moving. But if you are watching a movie, you have 30 pictures per second, and it will be impossible to transfer 30 full images per second from one process to another process and to see them continuously. They share the memory. So when you have big areas, it's necessary to do that. It's very just to speed up the process, and so this is a central point, and in many situations. Tomorrow you will discuss this method also for implementing the models for IPC that we have discussed in the early days of the ARP course. In the first class, I will propose you to work all together in doing that. So this is also a way of implementing one of the way we want to make process communicate, typical of big structures. How is it done? Well, always using the concept of file descriptor. So file descriptor, we can say that POSIX is file descriptor for everything. And is a strange and abstract way of considering it a file, but in any case, it's a file descriptor. So you have several system calls and a sort of protocol. So you have to call them always in the same sequence, like you do with sockets, in which you have the created sockets, you have to bind to and so on. And you have several system calls, and you have put them always. This is one of the reasons in libraries or classes, for example, you don't need to use them separately. You have just one class that does everything. But in any case, we are at a low level, so we must, and it's also important to understand why they are separated and what they do. This simply notices the system that you want a shared memory segment, referenced by a name, the name, and you have a file descriptor. For historical reason, I think, well, historical reason, for conceptual reason, since Linux kernel is completely based, linked with the file system. In that case, we have a directory that is a virtual directory in which there are no real hard files. In this directory, a file appears with represent the POSIX object and is created for persistence, since the once you bootstrap again, you can find the same structure. It survives the exiting of the processes. And another point is at the end of the fact, derived from the fact that you can use the same system code not only for sharing memory, we will see another picture, but we can do the dual thing. We can put in memory, or hold in memory a file. So in this case, we have memory that is represented by a file, by a virtual file, but it's real memory shared by two processes. In the dual case, we will see that a file, even if we use it as a file, is a memory file or memory mapped file. After you do that, so you have notice the system that you will use shared memory. Immediately after, you must say exactly which is the amount of memory that you use. This funny name is truncate, because in principle this is the whole memory, but you must decide, notice which is exactly the amount of memory they use. Then finally, this puts into operation the fact that the two memory segments are really superimposed. So I'll only one segment. Consider it as a way of asking the memory manager, that is an electronic part of the system, to find a piece of memory that you have decided how much it is, and to give the address of this memory to both processes. And surprisingly, if you know how the memory manager works, the two addresses are different. One process may say, okay, this common memory starts from address 100, and the second process may say, well, the memory shared starts from 1000. The two addresses are different because the two metrics of the addresses in the two processes are different, but they point to the same hardware location in the real memory. That's the reason why we have the third one. This talks directly to the memory manager. From now on, the two processes share the memory segment. After they have finished working, they do the two opposite function, that is unmap. So the two memory controller, memory manager are free to manage the addresses as they want, and then remove the shared memory segment. This operation is considered to be a real-time extension. Real-time extension memory is so it's a definition of real-time, very strict real-time, since what one process does is perceived immediately from the other by the other process. There is no buffer to transmit information. So it's this is the reason why you must compile with the special flag in the compiler that says we want to use the real-time extension of POSIX. The same you use for threads in general. Those of you, I suppose many of you that are working also on threads, and which, well, threads from logical point of view act in the same way, except that you don't need to map the two memory segments, because the when you do the create of threads, they share the memory that was already defined and the old data that has been defined before starting the threads. So mapping is included. Is not a way of doing the same mapping, because threads are in the same process. Here we force the thread model in different separate processes. So that's the main difference. Threads are also called lightweighted processes. So light processes, since when the scheduler runs the various threads, does a operation that is called the context switch, to stop one thread and start another thread, is lighter than stopping one process and starting a new process. So here is an example. We have an example. To be realistic, well, I didn't check in this last version, but I checked the other full example that is in the end of the slides. So you see, this main decides, it's just creating a file. So with the capability of creating and read, write, and all permissions. Who is allowed to work on this file. So this is typical. So this is a file descriptor. Once you have this file descriptor, suppose you want just to send a message, you have to truncate the file descriptor to the length of the message, and then to map. Once you know exactly how much memory you need, you tell the memory manager to provide the allocation of that memory in the whole main memory, and which is the parameter of size. The size typically is the dimension of the block managed by default by the memory manager. Here, something like 4,000 kilobytes. So it's very simple. Was the server. This is a sort of client. So once you have decided, which is, so you see here, typical dimension of a block of the block managed by default by so must be more than the size of the message you want to transfer. But in any case, you must say the memory manager, which is the physical block to be allocated. So you open, like you open a file, and do the same. Okay? And so you have the messages. You have the pointer to the memory, And so you can write directly, since it was built as a message in a string, and here in that case is just written as a string. These are instructions for, don't forget to use the real-time options. And the last one for today is, I haven't noticed it in advance, the same mechanism can be used to, not to make, try to make it a different process. It's not an IPC, but is useful because uses similar system calls, because the work carried out by the kernel is similar to the previous one. In this case, the idea is simply to map a physical file in the on memory. So sometimes we call the memory file RAM file, something like that. It's not necessary now to see that, but you must know that it's possible, and please read, and we can also discuss briefly. Very useful, because if you have files, you can use much faster access to the file, of course. Here is a text that probably you know, while it is reported here, because shared memory between processes is very similar to shared memory between threads. So logical entities who act on the same locations, and we need, as well as we need using threads, the concept of semaphore. Just use it for test your knowledge about semaphore if you're just attending also the real-time course. Semaphores in the semaphores in POSIX are the same semaphores for threads and processes, because in any case they are managed by the kernel. Also using threads, semaphores, or binary, or integer semaphores are completely managed by the kernel, because you know that wait and post operations cannot be implemented using code. They interact with the scheduler, and so there's no difference. The same semaphores, so you have to activate a semaphore, you have to use a semaphore, and then to dispose the semaphore after you have used it, because there are few semaphores available in the system. We don't have conditional variables that are typical of threads, but semaphores are the same. And you know why they are used, why they are needed. Open, wait, post, close, unlink, destroy the semaphore object. You see that in this case, you use the same switch in compiling with using threads. From this point of view, there's no difference between a semaphore in the threading and in using processes. And they act exactly in the same way, and they have the same suggestion. So use the minimum number of semaphores and destroy the semaphore as soon as is no longer needed, because they are valuable objects managed by the kernel. So a semaphore is a system call, even if you have primitives. So there is an example with the producer consumers in shared memory. So you can see a real example. That's all in this pack of slides. What is for pros? Can reduce memory usage. Big data structures can be mapped and shared to provide the same input to multiple processes. Okay, sharing may occur not only between two processes, but also between more than two processes, even if it's not so common. And input-output mapping can be very efficient. The example of images and the screen and the graphic server is typical of this kind. This is also one reason you don't have a graphic interface to your virtual machine on the cloud, because the graphic server, the typical graphic server in Linux is the X server, shares in memory with your processes that are communicating with Windows and so on. And you cannot share the memory with the remote process on the cloud. So that's the reason. There are several client-server models able to have a remote Windows, but absolutely less efficient than running the same server on the same machine. Memory access is really important, and when use I/O input-output mapping, for example, with a file, also by different processes, you can use semaphores instead of locking and unlocking records if you have concurrent access to a file. Locking and unlocking records, pieces of a file, you know that is when you open a file, the system call, there is a lock unlock. So if you want to write on a shared file, you have to lock the part of the file in which you write. If two processes write simultaneously, you will jam everything. Lock unlock for a hard file, for a real file, for a regular file, is much less efficient than simply using semaphores in locking memory, unlocking memory. Cons. The problem is that you see the granularity. When you specify the page size, you interact with the memory manager, which is part of the kernel, and in turn, the memory manager is cooperating with the electronic memory manager. And these all memory managers in all operating systems work with the concept of page size, so they cannot use a granularity less than 4 kilobytes, for example. So you cannot use memory mapping only of 200 bytes, even if they could be interesting. And so this kind of reserving pieces of memory is similar to reserving dynamic variables on the heap, or a file with many blocks all over on the disk. So the concept of fragmentation. Once you have used many blocks here and there in the memory, there are many blocks of memory free, but probably in some cases too small so that the memory manager cannot use them. So in any case, everything is good and bad. If you have to share big files or to share big structures, big files or big data structures between two or more processes, memory mapping is absolutely the correct way, even if there's no assignment on this. In the last slide, you have a code example with all comments, like the tutorial in socketing. Then you can grab and paste and compile and use if you want. Right? In any case, there are also comments line by line. and maybe we will say something more. Okay, that's all. Stop sharing. Hope that this discussion does not introduce strange concepts, and above all, I want that the concept, you can capture the important concept even if you don't use in writing programs for that. So I assume that you know which are all the uses of file descriptor in POSIX. So we can reverse the name of the course and say, this ARP is file descriptors for everything. And you must know, so in the last weeks, we will discuss again the file model in POSIX, taking also all the slides. Okay, questions?
Professor?
Yeah.
Would it be a good idea to use shared memory access? Well, if we had to, in the first exercise, to transfer this instead of that large array of data?
Sure, sure. It's absolutely a good idea. I didn't want to do that before because, of course, this is the last argument, and I'm not as, but using the, well, it's really a proper idea. Yeah, a good idea. That would be, unfortunately, too late, but it's a good idea. Nice question. If some of you will dare doing this example, don't look at me, Fedozzi. I'm not talking about of you. In any case, that's could be, if you had time, would be a good idea. Okay. I have a wall-mounted clock, and no, I think it's not 4 o'clock, but if no questions, I can say bye-bye and see tomorrow, okay? Tomorrow, I will ask you to work together, and we'll, okay, bye-bye. Thank you. Bye, see you tomorrow.
Nice evening, bye.
Thank you, Professor. Bye.
Thank you, Professor. Bye-bye.